Okay, new topic. And it's the beginning. This is undergrad level, senior level, but it's a topic that we will, if you keep following me to higher and higher levels, we'll go right through to PhD level. The topic, the idea is that there's a link, an intimate link, very deep link between the symmetry of your physical system. If there's a particular kind of symmetry, then that symmetry translates into a particular conserved quantity. Conserved means just doesn't change over time. So whatever it is, whatever this quantity is, it remains at that same value over time, doesn't change. So this session we'll introduce this idea starting at undergrad level, at senior level, and if you keep following me from level to level, next one be M1, first year master's level, and then M2. In fact, in a moment, well, soonish, I'll show you the texts. I'll hold up the books so you can see what's coming, and you'll notice that this idea of symmetry on the one hand and conservation, some physical quantity is conserved, doesn't change. Like one of the basic laws of physics is the conservation, in other words, doesn't change. The conservation of energy, right? Energy doesn't disappear, it doesn't suddenly increase or decrease. It's the total quantity of energy in a closed system, so long as energy is not coming in or going out into a larger environment, but within a closed system, so nothing gets in or out, then energy does not disappear. It's conserved. Like if you want to lose weight, then you need to keep this conservation of energy in mind, because there's like 3 ways you can lose weight. You can eat less, you can exercise more, or both. So there's three ways. So if you're inputting more food, which is just effectively energy, calories is just a unit of energy. So if your input of calories, of energy, is less than the energy you need to just live, heart beating, walking around, running, whatever, so that energy has to come from somewhere, that extra energy. So where does it come from? Well, it comes from stored energy, in other words, the fat on your body. So to generate the energy of moving for your body during the day, and if you're not eating enough to make up for that energy need, requirement for movement, then that energy will be taken from your fat, so you can lose weight that way. On the other hand, if your input of calories is greater than the motion energy that you need for the day, then where does that extra energy go to? What happens to it? Well, it gets stored as fat. Fat's sort of stored energy on the body. And now that made sense thousands of years ago when meals were often far between. But in today's world, it's a real problem. So there's a mass epidemic worldwide on obesity. Okay, so right now in classical mechanics, this idea that if there's some kind of symmetry in your system, there will be a corresponding conserved quantity. Now, to discuss it fully, we're only sort of touching on it a little, just scratching the surface a little at undergrad level. But in classical mechanics, it exists as well to some extent. For example, if your particle is moving in a central potential, what does that mean? It means that the potential V is dependent only on distance from the particle to the source of the potential. It might be another charged particle or something, or a nucleus, or whatever. So if that potential is a function only of V, of r, the distance between the source and the particle, then you will get the quantity that's conserved is the angular momentum. You get conservation of angular momentum when your potential is central potential to function only of r. So it's independent of the polar angles theta and phi, if you're talking polar coordinates, right? Now, if your physical system remains the same as you shift it, if you take a physical system and you move it along the x-axis by a certain distance, and if the physics doesn't change, you're just shifting it doesn't change anything, then the conserved quantity corresponding to that symmetry of position, whether it's here or here, that translates into conservation of momentum, and so on. Now, there's something similar type thinking in quantum mechanics, but before I get into quantum mechanics, at least the beginnings of it, let me say a little bit about this classical, because this idea in quantum mechanics that for a symmetry there's a corresponding conservation of something. That idea carried over from classical mechanics. Now, if you keep following me, I anticipate sometime next year, in 2013, I will start doing master's level courses, graduate level courses, and one of those courses will be on classical mechanics. I'll talk about Lagrangians and Hamiltonians and the Hamilton-Jacobi equations and all that kind of stuff. And I've done this before, but I'll use this text by Goldstein on classical mechanics, and as part of that course, you will learn about this mapping, if you like, between symmetries, certain symmetries in classical mechanics and their corresponding conserved quantities. And in quantum mechanics, higher level quantum mechanics, especially in something called QFT, quantum field theory, and in a moment I'll show you various books at various levels on that topic as well. Then, especially in quantum field theory, there's something called NOTER, well in English it would be NOE-THER. In German, because Emmy Noether, a woman, one of the rare women who's made top level contributions to her field. In fact, she's the only one I can really think of who's truly world class, truly deservedly famous, right up there with the best of them, of the males. She's the only one I know in both math and math physics. Emmy Noether. In German, it would be written N-O umlaut, that's the double horizontal dot, like those two dots in German are called umlaut, and it makes an O sound into an O, like a boat, O, an O sound, so Emmy Noether. Right? Well, a bit of a side. I hope you like my little asides. If you have a more linear mind, you probably get annoyed by them. But I have a somewhat lateral thinking type mind, so if you're the same, you might appreciate them. I don't know. Anyway, there's a bit of a story about her. So she came from a family of mathematicians. I think her father was a mathematician, and I think one of her brothers at least, also a famous mathematician, the Noethers. But she was the star, and the German colleagues used to joke about her, and they called her, behind her back, der, D-E-R, der Noether. Now you need to know a bit of German to appreciate the humour of that and its significance. Many languages, especially Indo-European languages, gendered, like nouns will be divided into male nouns and female nouns, and sometimes neuter nouns. Why this obsession to genderize nouns, I suspect, came from the discovery of paternity, way back thousands of years ago. The early gods were goddesses, in fact. But then, once agriculture started and husbandry, people started keeping animals, they discovered the concept of paternity, and then the miraculous property that women had of giving birth. They realized that men had a role in that. In fact, men started the process. So I guess they had a huge psychological boost on their ego, and so they just went crazy and genderized all their language as they were being formulated many thousands of years ago, like a millennium ago. That's my theory anyway. So German has 3 genders for its nouns: der, which is masculine, die, which is feminine, and das, like das Auto, the car. And so to call Emmy Noether, a woman, der Noether, is a kind of joke referring to her maleness, because she had a very definite male quality about her. I mean, just her face, the way she looked, and the way she thought. So the suspicion is that her brain, when she was in the womb, was highly androgenized, maybe a lot more male hormone from her mother at the time, and androgenized her brain, made her brain more male-like. That's the theory anyway, for what it's worth. Anyway, so Emmy Noether, famous name, Noether's theorem in quantum field theory, very important. So maybe now I could introduce some of the books talking about that. This is the undergrad quantum mechanics course, and you are very familiar with this book, the book that we are using at the moment. Now, first year masters, I think I've shown you this one before, will be called just simply quantum mechanics. Mandel, I like Mandel's stuff, so I'll be using several of his books. So you'll need to have quantum mechanics M1 level, first year